We now have two kinds of charge that we work with. There is bound charge, which is the result of polarization of a material, and often is in response to an electric field being applied to that material, and free charge, which is charge that we have moved around in some manner. The total charge is then the sum of the free charge and the bound charge. Now let's examine this in the context of Gauss's law. Gauss's law, or at least the differential form of Gauss's law, states that the divergence of electric field is equal to charge density divided by epsilon naught. Let's rearrange that a little bit, and we can say epsilon naught times the divergence of electric field is equal to the free electric charge density minus the divergence of the polarization, which remember is the bound charge. If we move this divergence of polarization to the other side, we get this equation. And since divergence is a linear property, we can use the distributive property to say that the divergence of this quantity here, epsilon naught times electric field plus polarization, is equal to the free charge density. We can then construct a new field called the electric displacement field and say that the free charge density is equal to the divergence of the electric displacement field. So, why would we want to do that? Well, like I said earlier, free charge is the charge that we move around. That is the charge that we create, decide where it goes. That's the charge that we put places. And bound charge is charge that is often the result of an applied electric field. It is sometimes easier to know what the free charge density is than the total charge density. And if we do in fact know the free charge density, and if that free charge density is in some form that is relatively easy to solve using some of the tricks we learned for Gauss's law, then it might be easier to use free charge density to solve for the electric displacement field, and then possibly use this to solve for the electric field later on if that is required. Now, some downsides. The electric displacement field is not just a scaled version of the electric field. There are a few differences. These differences are laid out in the textbook in section 4.3.2 on page 184. A couple of these differences. First, the electric displacement field does not have an analog to Coulomb's law. You can't say D is equal to QF over 4 pi epsilon naught r squared. Unfortunately, that doesn't work. Likewise, there is no analogy for electric potential. As noted in equation 4.25, the curl of D is not necessarily 0. And if the curl is not 0, then there is not a scalar field that we can do what we do to electric potential. So there are still reasons to use electric field. However, again, if the free charge density is in an arrangement that we know how to use Gauss's law, and if we are in the presence of a dielectric material, one where the bound charge will have a significant effect, it is sometimes easier to solve for D than for E.